Okay, chemistry students, here we are at the final lesson in Unit 4. We're going to deal with electron configurations or electron arrangements around atoms. So we have three objectives for you for this lesson. We'd like you to be able to draw orbital representations for the electrons around atoms, to apply the three rules for arranging electrons around the atoms, and we will be introducing those three rules in this lesson, and to make and use a diagonal rule chart, which you can use for showing the order in which orbitals will fill with electrons as we add electrons to atoms. This would go with reading section 7.1 in the textbook, so let's get to it.
Alright, the first principle we want to talk about is called the Aufbau Principle. And what this generally states is that you can add electrons to the lowest energy level of the orbital available. So what does this mean? Well, if you look down, you see the 1s here at the bottom. That is our lowest available energy level. So the electrons would start filling in here. As you add more electrons, it would go to the next available, which we see is the 2s, then the 2p, then the 3s, then the 3p, then the 4s. And something you see now, instead of going up to the 4p next, you see that the 3d is actually in between that. And that means that this would be the next lowest energy level, so we don't fill them up 1, 2, 3, 4, 5 energy levels. We actually have to fill them up in a specific way based on how the orbitals are aligned. So this also gives us insight. If you remember back in the last video, we had, I think it was what, the 3d orbital?
Right.
And then the n equals 4. So here you see n equals 4. But here is this 3d energy level in the fourth energy level on the periodic table. But since it's the third energy level, it's actually 3d. So it's slightly higher than 4s, but it's lower than 4p. So that's why it shows up the way it does on the periodic table. So let's show you a kind of a shorthand way of drawing this, because honestly, we don't want you sitting there and having to draw that tower out every time you want to do electron configurations. So we're going to show you the Aufbau principle, known as the diagonal rule.
Right, this is a little shortcut that we use. So you start by writing 1s, right under that write 2s, and just to the right of it 2p. Then underneath that, in the third row, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d. We could write 6f,
but there's none on the periodic table.
There aren't any elements that have electrons in 6f, so we'll just skip that, and then we'll go 7s and 7p.
Now the last thing we need to do with this diagonal rule, or second last thing, is we have to know how many electrons each sublevel can hold. The s sublevel, if you look at your periodic table, there are only two columns, which means s orbitals can only hold 2 electrons. So a good way, or at least at first, is to put 1s2 with a little superscript 2 there, so you understand that you have to put 2 electrons in there, and then for all the s's it's 2, and then for the p, there's 6, because, well, there are 6 columns, so take 6. D has 10, because there are 10 columns, and F has 14. So as you add those. And now it's called the diagonal rule because to do it, you draw diagonal arrows through each part.
So we're going to draw an arrow on a 45-degree angle through 1s. When you get to the arrowhead, then, you would go to the tail of the next arrow. So the second arrow goes through just 2s. The third arrow catches 2p and 3s. The fourth arrow catches like that, and then here's where we get to the overlap. So up until, so it would be 1s, then 2s, 2p, 3s, 3p, 4s. Then we catch 3d, 4p, and 5s.
Now you fill these in by going from end to the tip. So go 1s, then 2s, then 2p6, then 3s. So you go from tail to tip each time. and that's how you would fill in until you ran out of electrons to add in. So if you look here, you see the 2p, 3s, here's 2p, then 3s, and then you would hit 3p, 4s, well there's 3p, there's 4s, and then next you'd expect 3d, 4p, 5, so there that is. So that's how you would use the diagonal rule to your benefit, and you should be able to recreate this on any test you want, because we're not going to allow you to have this on any test. You have to recreate this diagonal rule to help you fill in.
We'll practice making it in class. It's not that hard.
And if you get good enough, you can just use the periodic table to do it,
right.
But that comes down the road. All right, let's go to the next principle then.
Okay, so the second rule for filling in the electrons around an atom is called Hund's rule. And this rule is simple. No electrons get paired up in a given orbital until all the orbitals on that sublevel are half filled. So we know that an orbital is a space that can hold 2 electrons.
Yeah, and we're looking at the D sublevel, so we know there are a total of 5 different orbitals, and they're denoted here with the -2, -1, 0, 1, and 2. And if you recall back to that periodic table, I think on page 31, we saw these -2, -1, 0, 1, and 2, and then basically we have a second thing to add. You see these down here, those arrows indicate electrons. The spin up one has the arrow going up, and that would be the first 5 elements in the D block.
Like the negative half spin.
Yeah, it would be for example, looking at the periodic table, it would be scandium, titanium, vanadium, chromium, and manganese would be the spin up electrons, and then the spin down ones would be iron, cobalt, nickel, copper, and zinc. So that's just a way to kind of write this in more of a condensed space.
So basically what we're saying is we have room, each box represents an orbital, and can hold 2 electrons, which we're going to signify with arrows. And if we wanted to put, let's say, give me a number between 7. Okay, so we wanted to represent 3d7 on here. We have room for 2 in each one, but Hund's rule is telling us we have to put 1 in each box before we put 2.
Exactly.
And so the way that we do it is we're going to put the upspin one first, 1, second electron, 3, 4, 5. Okay, now I have them all half filled.
So now we can start putting in.
Now go back 6, 7.
There you go. And that's how we do Hund's rule. And if you see one that has a pair before they're all half filled, you know it's an incorrect Hund's rule application. So just keep that in mind. That's how we're going to fill these in on our practice the next couple days here. So the last one is the Pauli Exclusion Principle, and we've already covered this one before, but we're just going to rehash it again and put it down in words for you. It just states that no 2 electrons can have the same 4 quantum numbers. If electrons are in the same orbital, they must have opposite spins. So if you remember, by the time we're doing the different postal addresses or the 4 different quantum numbers of any element, every element had its own set of 4 quantum numbers. This is exactly what the Pauli Exclusion Principle is telling us.
Yeah, if the electrons are in the same orbital, and the box here denotes the orbital.
Let's say this is the s orbital.
Okay, so if it's the s orbital, then we know that L is 0. And let's say we're on the first energy level, so we know that N is 1.
So that means we're dealing with either hydrogen or helium at this point.
And then we know that M sub L is also 0. So any electron I put in that box has those 3 quantum numbers.
So right now we know we're dealing with either hydrogen or helium because N equals 1, L equals 0, M sub L is 0. That's hydrogen or helium.
So that means the M sub S quantum number cannot be the same
for both hydrogen and.
So the way that we show that is the first one that we put in would have M sub S up, which would be, let's say, plus 1/2.
Yeah, and in this case, by the way we've been doing it, that would actually be helium, because the first half is negative. But that would denote either hydrogen or helium. And then the other one...
So this one would have N equal to 1, L equal to 0, M sub L equal to 0. But the spin quantum number, the M sub S, would be the opposite spin.
Exactly. So there we are. You can see that they can have 3 of the same quantum numbers, but the 4th one has to be different. Or 3 of the 4 can be the same, and 1 of them will have to be different. So that's how we apply the Pauli Exclusion Principle. Alright, so here's a real quick practice. This is not using the ground state electron configuration that we talked about briefly. This is just using an energy diagram. And the only time we're going to use these is if we give one to you, because drawing this, like we said before, would be a little
Not fun.
obscene. So right now we're going to practice this. In class we're going to practice the shorthand and the longhand electron configuration. So Mr. Ferguson, I want to start off with carbon. So
Okay.
we look at carbon on the periodic table. Its atomic number is...
That's not showing up very well.
That's
is
not
it?
showing up at all. Carbon's atomic number is 6, which
Okay.
means we know it has 6 protons. And in a neutral atom, it should have how many electrons? Then?
6 electrons.
6 electrons.
So I'm going to use my 3 rules.
So you start
Aufbau Principle, Hund's rule,
And Pauli
Pauli Exclusion Principle to put in 6 electrons. So the first 2 are going to fill in the lowest available, which would be 1s.
Yep. So there's 1.
There's 2.
There's 2.
And I use the Pauli Exclusion Principle because I put them with opposite spins.
Yep.
2s comes next. There's 3.
So they're still
There's
Aufbauing.
4.
That means they're building
Still
up.
Aufbauing. Okay, that's 4.
We filled that sublevel, so we
So-
have to go to the next.
So I have 2 electrons left, and they have to go into the 2p sublevel. And I'm going to put 1 there, but I'm not going to put the second one in the same orbital because Hund's rule says we got to half fill all of them
Yep.
first.
Okay. So now we have 1, 2, 3, 4, 5, 6 arrows. So we have 6 electrons. So carbon's done.
Okay.
Let's take it up to neon now, where we have 10.
Okay. So neon's atomic number 10, so I can keep the 6 that I already have.
So it'd be 1,
I need to
2,
add
3, 4, 5,
4
6.
more.
So we have to have 4 more. Yep.
Okay. So
Again, you have to add 1 to pair to
that
half
would be
fill
the
them all.
7th one. Then I'm going to go back 8, 9, 10.
There you go. And that would be neon's ground state
Electron
configuration. So let's do one more. That's a little more tricky, but not too tricky. Let's say vanadium.
Okay, so
Which is
vanadium is the
is-
atomic number
It's
23.
vanadium 23, yep. Or, yeah.
So it's going to have 23 electrons in a neutral vanadium atom.
So
I have
far
10
we have 10. We have to have
right
13
now.
more.
So I'm going to keep Aufbauing.
Yeah.
11, 12,
Yep.
13,
Watch where he's
14,
putting these arrows, because they
15,
are going in half-filled orbitals first.
16, 17, 18. So we end up filling 3p. Got 18
Yep.
electrons. I still have 5 more. 19, 20. I've
Yep.
completely filled 4s. And now we're going to, so 4s, we're actually started on the 4th energy level, but now we have to go back into 3d because that's actually higher in energy than 4s.
Yep.
And we
so
have
3 more to go.
3 more. 1, 2, 3. Hund's rule.
There you go. There's 3 examples of how to fill these in. These are by far easier than doing it the other way. That's why we're going to practice the other way in class.
We'll practice with orbital diagrams like this, and then we'll go to the longhand electron configuration, and then we'll teach you the shorthand,
Yep.
aka noble gas configuration. You guys will be experts by the time we're done.
We hope so. Right. Have a good night.
All right. Okay, so for the post-video question, I kind of have the same question posed for 2 different elements. I want you to use those 3 rules, the Aufbau Principle, Hund's Rule, and the Pauli Exclusion Principle, to kind of make the little orbital diagram like I have shown there and show the arrangement of electrons that would be found for each of the elements shown. So on the left I've got nitrogen, and on the right chlorine. So I've given you probably more than enough orbitals, like there's going to be some unfilled orbitals in each one of these, but fill in the electrons. Remember, we're going to use little up and down arrows like such, like up and down arrows to represent the electrons in an orbital. So see if you can do that for the elements shown, nitrogen and chlorine, and we'll see how you made out with that tomorrow or the next time we meet. See ya.